Okay, let's talk about operations with these complex numbers in polar form. I think we'll save it for class. We're going to go through a proof of what I'm about to show you. So we're kind of go backwards. I'm going to give you the format for how we do it. Then the next time we meet, we'll go through a proof of why this works. I know that's backwards, but I want to keep your interest as long as possible. The proof is kind of bonkers. Okay. So if I have two complex numbers, z1 and z2, all right, I've written z1 with its modulus r sub 1 and its argument theta sub 1 like this, and then z2 is here. If I wanted to find the product of z1 and z2, if I wanted to multiply these two things together, I would be multiplying these two things together. And that's where we'll do the proof. But for now, I'm just going to show you the shortcut, and that is we multiply the moduli together. Say that 5 times fast. We multiply the moduli together like this, and then inside here, we're going to have the cosine of the sum of the arguments. And then we have the sine of the sum, I'm running out of room, of the arguments as well. Sorry, didn't think that out very far. So we've got the product of R1 and R2 here. And then inside here we're actually adding. And the way that I've always just kept this straight is when you think about exponents, right? When you're multiplying terms that are powers, like a squared and a squared, what do we do with those two numbers? We add them, right? So like addition and multiplication, they're like sister operations, sort of. So there are times we've done this with logarithms, we've done this with exponents, because logarithms are exponents. But when you're multiplying, sometimes you also do some addition in the problem, and that's a very loose connection here as to why we may have, we can write this as a sum. Okay, so this is how we multiply two complex numbers together. So here's an example. Okay, suppose I have z1 and z2, oops, backwards. z1 and z2 that look like this. Here's my r value right here. Here's my theta value, so the modulus and the argument for the first number, the modulus and the argument for the second number. If I want to multiply those two numbers together, the product of z1 and z2, I take the moduli and I multiply them. And then over here, I take the arguments and I add them. So that was 2 pi over 3 plus 11 pi over 6. And then I've got the sine values here. Same theta values, right? Same arguments in both of those. Okay? So if we clean this up a little bit, I'm going to jump over so that I give myself some space. 2 times 8 is 16. Now in here, I've got the cosine of 2 pi over 3 plus 11 pi over 6. Maybe I can slide this down. Okay. 2 pi over 3 plus 11 pi over 6. If I'm going to add these together, I need a common denominator. So I'm going to multiply the top and bottom here by 2. So that's 4 pi over 6 plus 11 pi over 6, which is 15 pi over 6. And 15 pi over 6 reduces to 5 pi over 2. And we're going to keep going because 5 pi over 2 is greater than 2 pi, right? It has a coterminal angle that is less than 2 pi. What is 5 pi over 2 coterminal? Pi over 2. So this is pi over 2. I was waiting for Miss Epitello to respond, but she didn't. She's doing her own thing over there.
Pi over 2.
Pi over 2. So we have the cosine of, we did this addition, we simplified it all the way down to pi over 2. So we're putting that in here. We don't have to go through that exercise twice. We're going to get the same thing here with this sine term. So we have the sine of pi over 2. Now, when you look at this, pay attention to the blue font in MathXL, or the directions, if you will, okay? Because if they want the polar form of the number, we can stop here. We have the new modulus, we have the new argument, we can stop. But they may ask for this in standard form. If they ask for this in standard form, we've got to calculate this. The cosine of pi over 2 is the x-coordinate at pi over 2, which is 0. The sine at pi over 2 is the y-coordinate at pi over 2, which is 1. So we end up with 16 times 0 plus I, which is 0 plus 16i. So here is our standard form of that complex number that we get. We get that by calculating the polar form. So we have this. Here's our polar form product. Here's our standard form product. Okay?